So in this video, we're going to look at our first actual full example problem involving a case of static drive friction. So we're given a car and we're told its mass and we're told the coefficient of static friction between the wheels of the car and the actual surface of the road. And what we're told is that we're pulling it at a 30-degree angle and we're curious to find the smallest magnitude of the force F that needs to be applied in order to move this car if the back brakes are locked and the front wheels are free to roll. Now, part of being good at this problem is understanding how kind of those restrictions that are summarized there, the back brakes being locked and the front wheels free to roll, actually manifest themselves in a free body diagram, which we'll see here in a minute. So before we actually draw this free body diagram, let's think about what's going on. We have the actual weight of the car, which we can compute given the mass by multiplying by the constant acceleration due to the gravity. We will apply it at the center of gravity in the downward direction. So we have the downward Y force associated with the weight. At both of the wheels, we'll have a normal force, which is pointing purely in the upward direction at both the front wheel and the back wheel. So we'll have two normal forces there. In addition, the way that we're going to account for the friction between the wheels and the road is since the back brakes are locked, meaning that those wheels can't actually roll, note that the back wheels would slide relative to the actual ground. So we will actually have a frictional force there that's going to oppose the motion associated with the applied force F. Notice that this applied force F at a 30-degree angle has a component in the horizontal direction, which is going to pull the car to the left, and also a component in the vertical direction, which is going to serve to reduce the required normal forces because it's going to offset some of the weight and is going to reduce the maximum static friction force. So it's going to be easier to pull because of that, as we'll see in a minute. But key point is at B, we're going to have both the normal force that we already mentioned, along with the frictional force that's going to be going to the right to oppose that motion of the applied force. However, at wheel A, since what they mean when you work these kind of problems and they say that the front wheels are free to roll, that means that you have no frictional force actually pointing to the right in that direction. So when we draw this free body diagram, that's exactly what we see. We have the two normal forces at both sets of wheels, only a horizontal frictional force at the back wheel where the brakes are locked. We have the applied force F, and we have the weight. So let's think about whether or not this is statically determinate, right? We don't know the two normal forces. In addition, we actually don't know what the magnitude of this applied force is. We're trying to compute it such that we find the minimum value required to make this car move. And remember that physically what make this car move means is to make that force equal to the maximum static friction force. So we actually don't know F, we don't know NA, we don't know NB. And in addition, we can't compute what FB is because FB is going to be related to the normal force NB. So we actually have four unknowns here. And remember that in a coplanar force system or a two-dimensional statics problem, we can only write three equations of equilibrium. So you might look at this and think that it's statically indeterminate. However, remember that we know a relationship between the applied force F and the actual static friction force FB. So that's going to be that extra equation that we need in order to resolve this system and solve for the fourth unknown. So let's look at enforcing the equations of equilibrium in the horizontal direction. We know that the sum of all forces must be equal to zero. That basically tells us that if this thing is just at the point of impending motion, if it's not slipping yet, because remember what happens, think back to that graph that we showed where the frictional force is constant through the point of impending motion, and then it drops when this car actually stops moving. So if we're thinking about the point of impending motion, we're just pulling it hard enough to get it to slip, at which point the actual frictional force will drop down. We know that what must be happening is the frictional force at B, which is going to the right, is going to be equal and opposite to the horizontal component of the applied force F. So FB going to the right, and then we decompose the X component of F by just multiplying the magnitude, which we don't know, by the cosine of 30. And that must be equal to zero since those are only forces acting in the horizontal direction. In the Y direction, we have the two upward normal forces along with the component of the applied force in the upward direction. Notice that that will be opposite the 30-degree angle. So that's multiplied by the sine of that angle. They're going up. What's going down? Well, this is just the weight of the car. It's the mass, since we're in SI units, times the acceleration due to gravity. Finally, we need to enforce one rotational equation of equilibrium. How should we do that? Well, it doesn't matter really whether you sum all moments about point A or sum all moments about point B. Both are going to be equally easy problems because if you do it about point A, notice that, of course, the normal force at A won't contribute to rotation about that point because its line of action goes directly through, but so does the frictional force. If you were to extend that line of action, notice that it goes through point A as well. So if we sum all moments about point A, we notice that if you have your car and you consider the rotation caused by the normal force at B about A, that is in a counterclockwise direction. So the sign convention for NB will be plus. NB, the perpendicular distance from the point A to the line of action of NB, is just this 1 meter plus 1.5 meters. That's where the 2.5 meters is coming from. We need to do the same thing for the actual weight of the car. Let's first determine the actual sense of the rotation. Notice that if you pin at A and you push down in the weight, that's going to be clockwise rotation, meaning we need to assign a negative value. We computed the magnitude of the weight above, and the perpendicular distance in that case is just going to be 1. When you actually consider the applied force F, it's easiest to treat this in two parts, decompose it into a vertical component. Note that a vertical component is going to induce clockwise rotation. So the component that's related to the sign is going to have a minus in it because it's introducing clockwise rotation. And in that case, the perpendicular distance is just this 0.75. And the horizontal component, if you pin and do our traditional technique for determining sign, you will see that it induces counterclockwise rotation, so it is positive F cosine 30, and the perpendicular distance there is just the radius of the actual wheel. That's why you're given that dimension. So this system alone is not, it's indeterminate. You can't solve it. 3 equations and only 4 unknowns and only 3 equations. So in order to have an additional equation, we simply say that in order to move this car in the case of impending motion, we need the actual frictional force here, in this case, to be equal to the maximum frictional force, which will be just 0.3 times NB. Remember that 0.3 is the coefficient of static friction, so the frictional force is just between that back wheel and the road. So we know the coefficient of static friction, and we can solve for this normal force NB. So basically what we did is we expressed the thing we didn't know, FB, in terms of another thing we didn't know, NB. So with all of those equations, we can solve them simultaneously. And what you'll find is that you have to apply 2.762 kilonewtons of force in order to get this thing to move. And solving the equation simultaneously, you can also find the expressions for the normal forces along with the frictional force in this case. So hopefully that made sense, and we'll look at some actual problems from the homework in the next few videos.